Hi, I'm Manish Shirke and this is my Capstone Project, the Autonomous AI Ops Engineer. It's built for the Enterprise Agents track and it automates detection, diagnosis, and remediation of cloud incidents using a multi agent architecture. Modern cloud infrastructure is becoming impossibly complex. When a critical service fails at 3 a.m. in the morning, the traditional response is a sleepy on call engineer digging through logs, trying to find a needle in a haystack. SREs spend hours triaging logs and metrics. Manual incident response is slow, stressful, and error prone. Rigid automation scripts fail the moment they encounter an error they weren't explicitly coded for. We need a system that doesn't just follow the rules, but reasons about them. We need infrastructure that heals itself. The solution I have built cuts the mean time to resolution by reasoning about issues, calling tools, verifying fixes, and learning from past incidents. This is where AI agents change the game. Unlike standard scripts, which are brittle and stateless, agents utilize probabilistic reasoning. For this project, I have built an autonomous AI. It can monitor signals, analyze patterns, call tools, observe results, replan, and collaborate. It uses Retrieval Augmented Generation RAG to recall how similar incidents were fixed months ago. It adapts its strategy in real time if a fix fails, and it's ideal for dynamic incident resolution workflows. Agents bridge the gap between human intuition and machine speed, turning unknown errors into solved tickets. I architected this solution using the AI operator pattern. Now, this is inspired by the Kubernetes operator pattern, where a controller watches the state of your system and acts to reconcile it with the desired state. But instead of hard coded logic, our controller is a cognitive engine. At the core is the orchestrator, which I am showing in the screen basically. So, this is the orchestrator. Think of this as a manager. It is a state machine that maintains the life cycle of the incident. It holds the context, tracks the current states, and coordinates 5 specialized subagents. So these are the 5 specialized subagents, as you can see. The monitor agent, the diagnose agent, remediate agent, verify agent, and the report agent. So the orchestrator is the one that holds the context and tracks the current state and coordinates the 5 specialized subagents. Now let's walk through this flow. So first, the monitoring agent. The monitoring agent basically, this is the eyes of the system. It ingests raw alerts from tools like Prometheus or PagerDuty. Its job is noise reduction, filtering out transient alerts and passing only confirmed signals to the orchestrator. Next is the diagnosis agent. Now, this is the analyst. It doesn't just look at the error, it looks at the history. It queries a vector database to find similar past incidents. So if we saw a database timeout 3 months ago that was fixed by a restart, this agent retrieves that context. It performs a root cause analysis and proposes a hypothesis. Then comes the remediate agent. Now, this is the hands of the system. It takes the diagnosis and formulates an action plan. Crucially, it uses the Model Context Protocol (MCP) to safely interact with the infrastructure tools. So it uses MCP to interact with the infrastructure tools. So basically, this is the tools, as you can see over here. And currently, we have coded for restart service and scale pods. These are the two tools that we have provided as part of this, project. But this can have many more, tools, uh, they can be provided, and those can be invoked basically using MCP by the Remediate agent. So now this Remediate agent is the one that calls this tool using MCP. So it can call it to basically scale a Kubernetes pod or to restart a service. It can also pause for human in the loop approval for destructive actions. So basically, as you can see here, we have shown a HITL gate, which is a human in the loop. So what happens is basically the remediation agent waits basically to get an approval from the human before it actually does a destructive actions, just like a restarting a service. So it'll ask the human, is it okay for me to restart the service? And if the human says yes, then basically it goes ahead and restarts the service. If the human says no, then it doesn't restart the service. So let's say the remediation agent is able to call the necessary tools to fix, or remediate the issue basically. Then the verify agent is called. So verify agent steps in. This is our quality assurance. It rechecks the metrics. So it rechecks the metrics. Did the latency drop? Did the error rate hit 0? If the answer is no, it triggers the orchestrator to loop back and try a different strategy. So let's say, it still says, oh, still the issue is there. Then it tries to loop back again and see, if it can find another solution, basically, to try a different strategy. This closed loop verification is what makes the system autonomous. So it will keep on trying till it fixes the issue. Finally, the reporting agent, the scribe. Once the incident is resolved, the reporting agent summarizes the entire timeline into a post-mortem document and saves it back to the memory bank. This ensures the system gets smarter with every incident it solves. By decoupling these capabilities into specialized agents, we create a system that is resilient, scalable, and safe. The autonomous AI ops engineer moves us from reactive firefighting to proactive self-healing operations. So now we will go through the demo for this autonomous AI ops engineer project. So basically, I'm going to use my Kaggle runbook for this. So as you can see in this Kaggle runbook, I have explained this autonomous AI ops engineer. It's part of the enterprise agents track. So basically, it's actually based on the AI operator pattern, event-driven AI operator pattern. And it actually uses the LLM model Google Gemini 2.5 Flash-Lite. So it is coded in Python, basically. And the technologies that we are using is Python, Google Agent Development Kit, and there's a Google ADK, and the Gemini 2.5 Flash-Lite is the LLM model that we are using. And for persistence, we are using the SQLite database. And the system relies on a custom-built observability engine for telemetry. So basically here I've tried to describe basically the various agents. So as you can see, the monitor agent ingests raw alerts. Diagnosis agents performs root analysis. And the Remediate agent formulates and executes action plans using the tools. And then the verify agent validates the system health post-remediation. And the report agent summarizes the incidents and archives knowledge. So basically, I have tried to describe, in detail. And this is, as you can see, is the file structure for our code. So basically, we have this is the AIOps agent basically, and in this we have the config.py, which is the centralized settings and constants, and then we have the main.py, which is the entry point, and then we have the orchestrator, which is implemented using this ops_orchestrator.py. And now this is the brain basically. This manages basically all the sub agents. And then we have the interface, the adapters. This is the Gemini adapter.py. And this is the one which connects logic to the LLM and also handles safety and tools. Infrastructure. Now this is the backend. So in this we have the message bus.py. So this basically is doing is in-memory pub sub for agent communication. So it is using A2A, agent to agent. For agent to agent communication, it's using in-memory pub sub. And then we have statestore.py, which is the logic for the SQLite database. Connecting to the SQLite database, and also the compaction logic basically for compacting many of the data that comes through. So basically that gets compacted. And then this is the observability engine, which is the ICE, which is doing the tracing, the spans, and the dashboard generation. And here is the prompts. These are the instructions to the LLM. So strict system prompts, and also we have provided negative constraints. So like make sure you don't have you don't look at an error input. So basically that's some of the negative constraints. And then this is the tools, which is the actions.py. Now this is the one which does things like restart the instance or scale the pods basically. So restart server or scale the pods. So here we are going to talk about a sample execution. So in this case, the user inputs payments API experiencing latency spikes. So in our implementation, this user input is simulated by programmatically constructing an Google ADK event object rather than requiring real-time user interaction. And then as part of the observe, the monitor agent logs this incident to the SQLite database, which is our facts table. And then the diagnosis agent queries the SQLite database and finds that scaling pods fixed this issue 3 months ago. So basically diagnosis agents is now trying to find out what could be the possibly issue. And so basically it queries the SQLite database to see if any such incident occurred. And similar to this happened before. And it finds, and when it was searching, it actually found that there was an issue which was fixed 3 months ago. And that was done by scaling the pods. So then the diagnostic agent outputs a plan, scale pods. And then the remediation agent attempts to scale. And then the system pauses because, when it's trying to attempt to scale, the system pauses so that the human can provide, approval. So you get on the console, you get approval required, execute scale pod. So it's actually waiting for the human to say yes or no. The human types yes. Now for demo purposes, we will be auto-approving by simulating the user typing Y and approving the task execution. The next is the tool executes latency. So basically, once the human approves, then we call the tool, and then the tool executes. So for instance, in this case, scale pod, and then it returns, deployment scaled. Next is the verify agent. Verification agent basically reads the tool output and confirms that yes, the pods have been scaled. Then archive. Now the reporting agent saves this new successful fix to SQLite database for future RAG, basically. So let's look at the notebook, basically. So first we need to do is authenticate in the notebook. So in the API key, so you must add your Google Gemini API key. And then you need to run the cell below so that to access the Google API key, you just save it. So basically, we will just, run. So as you can see, it is running now. So once it is this Google API key is set up, then it will say set up and authentication complete. Next, we want to install this the dependency. So we need to install the Google Generative AI for LLM and the nest underscore async IO to run the agent loop inside Jupyter. So we'll also validate the install was successful. So let's do that. So this is installing, the generative AI. So as you can see, it was executed. Now let's just make sure that it was indeed done. So see, environment is ready, and we also see the Gen AI version. So environment is ready for the agent. Now this is basically, we are creating the directory structure. So we previously went across the directory structure for our AI ops agent. So this is where it's getting defined. So project structure created at the AI ops agent. Next is the configuration, basically centralized settings for the agent. So here we have the database name, and this is the primary model, LLM model that we're using, Gemini 2.5 Flash-Lite. And this is a fallback model, Gemini 2.0 Flash-Lite. And then we'll try maximum 3 times. And this is actually the number of incidents to keep before compacting the history. And this memory limit is 3. So let's run that. Okay, so we have the config.py. Now next is the observability engine. So this is actually a custom telemetry system that traces spans and latency. It calculates token usage and generates dashboards. So let's set that up. So it's the executed basically. So that's the engine.py class. Engine.py Python program. So basically we have set that up. And then basically this is the infrastructure. We have the state store.py in the infrastructure part, components. Now what this does is implements persistent memory using SQLite. Also includes context compaction logic to summarize old incidents when memory gets full. We're gonna run that. So that will create that file for us, state store.py, which is a Python file. It's executed. So next is, as part of the infrastructure, we also have the message bus. This decouples agents using an in-memory pub/sub queue. So this is how agents communicate with each other. So we all create that file also, messagebus.py. And then this is the tool implementation. It contains the actual infrastructure tools functions such as restart service, scale pods. Now currently we only coded for restart service and scale pods, but you could have many more. So let's create that file. Let's create. Now these are the prompts basically. So they contain the system instructions for each agent. So each of these agents, basically, we need to provide system instructions. So these are the system instruction for each. Also note the negative constraints in the prompt diagnose to prevent hallucination. So we provide the negative constraints in order to prevent hallucination. So let's go over some of these prompts. So let's first create that file, agentprompts.py. So let me run that. Yeah. So as you can see, let's go over the prompt monitor, right? See the prompt monitor. So what we are saying is, if you look at the prompt, it says analyze severity. If critical, save to database. And then this is the DB write. And this is how it shows save to the database, DB write, and then status, and then active. So basically what it is telling is, it's actually, this is the prompt to the LLM, the Gemini LLM. The monitor agent basically will be, invoking the Gemini LLM with this prompt. Now the diagnose agent has this prompt, diagnose prompt, which is, so what it says, you are the brain. So it asks the, LLM to first read the rack history. If past fixes exist, use it. So if there are any past fixes, that you are able to retrieve, then use those. If no history, then default to restart service. So for now, if we don't have any history, then we just default to restart service. And then we provide valid tools, like, we are giving it a list of tools that we are having, the restart service and scale pods. And we also are giving some, negative constraints in the prompt, like for instance, invalid steps, do not output check logs, check history, or investigate. And this is the reason, we are providing this is so that it doesn't hallucinate, basically. So basically what happens is, let's say the LLM were to come up with a response saying, other than the restart service or scale parts, then, and then basically it doesn't find, that, particular, as a valid tool, basically. And then basically, so that's why we are putting this negative steps, so that do not output check logs, so because LLMs can tend to hallucinate, and if they, let's say, are not able to find a tool, they'll make up a tool, basically. And next is the prompt remediate. Basically, this is the remediate agent, basically, and this is having this prompt, execute plan, and then output in this format. So basically it creates a plan and then executes it. And this is the verify agent, basically. So for the LLM, it has this prompt, analyze tool output, if success result true, and then output in this format. And then we have the reporting prod, which is actually, used by the reporting agent to, it uses this prompt with the Gemini LLM. Summarize, it tells the LLM to summarize, and then archive in this format, basically. So as you can see, we already, generated this prompts.py. So the next is this, Gemini adapter.py. Now, this is the core driver that connects the Python code to the Gemini LLM. So this Gemini adapter is the core driver that connects the Python code to Gemini LLM. It includes the human in the loop safety check. Please note that for demo purposes will be auto approving. So, even though we have this human in the loop safety check, for our demo purpose, we will be auto approving. So in this code, we'll simulate the user typing yes for approving the task execution. So let's actually create this file. So I'm gonna run it. So basically this should create the, Gemini adapter.py. And so as you can see, it's telling it the model, which is the primary model, which is, the Gemini model, basically. And this is where we actually, have the hard-coded mock approval, basically. So here it says approval required, basically, and then it simulates the, user simulated typing Y, basically. Okay, now this is the orchestrator. The orchestrator, it defines the orchestrator class which inherits from base agent. So this orchestrator is the one which manages the loops. So it's actually orchestrates all these, 5 agents that we had, the monitor agent, the diagnose agent, the remediation agent, the verify agent, and the reporting agent. So it manages the loop and calls the individual. So here we have actually, as you can see, have run this particular agent, the main.py. And as you can see over here, this is actually seeding database to demonstrate RAG and compaction. So here incidents have been saved to history, basically. And so it's actually just creating, seeding some incidents, basically, into the database. And then basically starting this interactive session, payments API experiencing latency spikes. So simulating this issue, saying this payment API application is experiencing latency spikes. And then the orchestrator, basically gets this input, and then it invokes the monitor agent. So the monitor agent basically, then invokes the diagnose agent, and then the diagnose agent basically, creates a plan, and then actually sends it over to the remediate agent. And the remediate agent says, okay, let's restart the service, basically. As you can see, so it's saying restart service. So basically, then if we have to do something like restart service, then human approval is required, basically. So this is where it actually, we are simulating that the user is providing, approval. And once the user provides the approval, then as you can see over here, that, the service is restarted. And then if the service is restarted, then basically after starting up the service, we need to verify. So the verify agent is pulled in. And then it verifies that, yes, indeed, the service has been restarted and the issue has been resolved, basically. So basically, it then reports it to the reporting agent, which says, okay, the issue has been resolved. So it actually, archives this particular incident in the database. And then this is actually, we are creating, what is the latency, basically, and how much tokens were used, because, we are using the LLM agent, right? So for this LLM agent, with the Gemini model, how many tokens are we using? So that's it actually calculates that, because there's a cost involved, certainly, even for the LLM agent. And then basically, this is a dashboard, that observability dashboard that we have created. So as you can see, we are showing, the latency for the monitor agent, the diagnose agent, the remediate agent, the verify agent, and the reporting agent, basically. So these are the latencies, as you can see here. So total latency was about 5.37 seconds, and then our session was completed. So in conclusion, this Capstone project, Autonomous AI Ops Engineer, successfully demonstrates. So this Capstone project successfully demonstrates the transition from Gen AI chatbots to agentic AI ops systems by implementing the AI operator pattern. So the autonomous AI ops engineer we have built does not follow hard-coded if-then rules, but instead it observes the infrastructure, it looks at the infrastructure, reasons about that particular infrastructure using historical data, negotiates a plan, and safely executes it under human supervision. So that's the full details of my capstone project. I'm Manish Sharkey, and I thank you.